So the first step will be to create the metric in the space um, x hat d hat. Okay, and as I said before, we are focusing on Cauchy sequences in the metric space XD, right? So this space x hat is a space of all Cauchy sequences, right? All the Cauchy sequences in this metric space. Okay, so how do I define the distance between two sequences xn and so let me write not xn, but let me write this as x hat and y hat, right? So it's the distance between two sequences, right? It's the distance between two sequences, not the number, but distances between two sequences, where and moreover, it's Cauchy sequences, right? So how do I find the distance? It's nothing but, let me define, right? Let me define this as the limit n approaches to infinite, distance xn yn. Okay, distance xn yn, where xn is the sequence, is nothing but the sequence, right, which we picked x hat, right, and yn is the sequence y hat, right. So you're just taking the nth term xn yn, you calculate the distance in our original distance metric, right, and you calculate the limit, right. This will now the question is, well, do we even have this limit, right? That's the question. Does the limit exist? So, and if so, then the problem is it a valid metric? Does it define a metric at all, right, in this space? So there are a lot of problems, so we'll go step by step. So the first thing is to show that this limit exists, right? Okay, so let's pick the, let's start with this one, distance xn yn, right? Well, what can we do here? We can definitely use the triangle inequality, distance xn and xm plus distance xm ym plus distance ym yn, right? What I've done is I've just introduced another point xm, so it's in the same sequence, the mth term. So this is the nth term, this is the mth term, this is the mth term of y, right, the sequence here, and this is the nth term again in the sequence here, y hat, right? Okay, so this is just triangle inequality. This is triangle inequality. So let's bring this here to the left hand side and see what happens. So this is distance xn yn minus distance xm ym is bounded above by distance xn xm plus distance ym yn. Well, this is good. One thing I want to point out is that there's nothing special about starting with n, right? You could have started with m as well, right? So instead of n, if I had started with xm, so xm ym, and I'm using the triangle inequality by introducing the term xn, well, that's completely fine. I can do that, right? So distance xn, you have distance xn, distance between x and yn plus distance yn and ym. Well, this is perfectly fine. This is perfectly fine. And so if you bring this to left hand side, what happens this time is distance xm ym minus distance xn yn is bounded above by distance xm xn plus distance yn ym. Okay, well, let's compare this one and this one. You will see that the right hand side is the same thing. So distance xn xm, distance xm xn, well, they are the same. We know that in distance it's symmetric, right? You can flip it. So distance xm xn or distance xn xm is the same thing. Here also is the same thing. So the right hand side is the same. The left hand side is what's the difference here? It's distance xn yn minus distance xm yn. Here distance xm ym minus distance xn yn, right? So it's just like one of them is the negative of the other one, right? So what this implies is that in the absolute magnitude. So if we just take the absolute magnitude of, let's say, xn yn minus distance xm ym. So if you take the absolute value of this, distance xn yn minus distance xm ym, this is bounded about by the same thing, distance xm xn plus distance yn ym. Okay, so this is what we get. Next part of the proof is that remember, this is all Cauchy sequences, right? So we are playing in this field of all Cauchy sequences from our original space X. So notice that this particular distances that we have calculated, it's extremely small, right? These are extremely small. If you choose m and n appropriately, so if m and n are extremely large, this can be made extremely small. That means you can write this goes to 0. Okay, so that means that this particular sequence is also Cauchy, right? So the sequence distance xn yn, right? So this is a sequence, right? This is a sequence. How do you define the nth term? It's distance xn yn. How do you define the mth term? Distance xm ym. So this itself is a sequence, right? This itself is a sequence, and it is Cauchy, right? This is Cauchy, right? So this is a Cauchy sequence. It follows because of this inequality that we have here. So now, what kind of sequence is this? This is real number, right? This is a Cauchy sequence in real line, right? Hence, it converges because R is complete. R is complete. So any Cauchy sequence here converges. So this converges, okay? So this converges. What does that mean? Limit n tending to infinite, distance xn yn exists, right? This exists. And we started this as the definition of two sequences x hat, y hat. Okay, this was our definition, and this exists. Okay, that's good. But the problem is that if you go up, and if you look at the proof here, what did we do? We picked a sequence from this. Okay, so what we did here was to pick a sequence from this equivalence class x hat, right? So this is an equivalence class of all sequences or all Cauchy sequences which are related to each other, right? So that's how we define this here. So you pick a sequence xn, yn from these two equivalence classes x hat, y hat. And what's the distance here? You just calculate the limit n tends to infinite, distance xn yn. Well, what we have shown here is that this exists, right? For any two Cauchy sequences, this quantity exists. Now the question is this properly defined, right? If I pick two other sequences, right? If I pick two other sequences, let's say xn prime, yn prime, from the same equivalence class, right? From the same equivalence class x hat, y hat, if I calculate the distance, and if I calculate the limit, am I going to get a different number, right? If I'm going to get the different number, then this is not a proper definition of the distance between these two equivalence classes, right? But if it happens that the limit of this distance between any two other sequences from these two equivalence classes x hat, y hat, if the limit is the same, if it happens to be the same, then this is well defined, right? So that's the definition. So you can pick any two sequences from two equivalence classes, you calculate the distance, calculate this limit, that's the limit, right? That's the distance between two equivalence classes x hat, y hat, right? So that's exactly what we are going to do now. We're just going to go down. We are going to see if it is true that, if this is equal to limit n approaches to infinite, distance xn prime, yn prime, right? Okay, so where xn prime is another sequence from this equivalence class x hat, or yn prime is another sequence from this equivalence class y hat. Well, it's not too difficult because we have an inequality here, right? This is an inequality that we have here, but here you see it's xn, yn, xm, ym. So when we use this triangle inequality here, what we did was we introduced xm and ym, right, to create this triangle inequality. But instead of introducing xm, I can actually introduce xn prime, right? I can introduce xn prime here, and here xn prime, here yn prime, here yn prime, right? So the same triangle inequality, instead of writing xm and ym, I can just introduce xn prime and yn prime, and the inequality holds here, right? Inequality holds here. So the same is the case here when you start with yeah, so once you have this one, right, once you have this one with xn prime and yn prime, you also have this particular inequality from which, I will write the combined one, so it will become much more clear there. So distance xn yn minus distance xn prime yn prime is bounded about by distance xn prime plus distance yn prime. Okay, so it's the same thing here. It's the same thing that we have here. Okay, it's the same inequality, but instead of xn and xm, what I've done is it's xn yn, xn prime yn prime. So you will see that you get the same thing. So if you want, you can actually check it for yourself again. It will turn out to be the same sort of inequality. Okay, now what do we know about xn and xn prime? Xn and xn prime, they are from the same equivalence class. What about yn and yn prime? They are also from the same equivalence class. So if they are from the same equivalence class, what that means is the limit n tending to infinite distance xn prime is 0, because that's the definition of that's the equivalence relationship that we use, right? We say these two are related to each other, or these two are related to each other when you calculate the limit of the distance between xn and xn prime. If you take the limit, it goes to 0, then that means they are related. So that means this term goes to 0, this term goes to 0 as your n becomes larger and larger, right? So what that implies is that this term, right, this quantity here also goes to 0. It can be made into extremely small number. So that means limit n tends to infinite, distance xn yn should be equal to n tends to infinite, distance xn prime yn prime, right? So it's the same thing. The limits are the same thing, right? So this shows that it doesn't matter, right, what sequence that you pick from an equivalence class, the distance is the same, because these two limits are the same, right? So I can definitely define the distance between two equivalence classes to be just this, right? Pick any two sequences, maybe this one, right? Or this one. It's your choice. Doesn't matter which one you pick, but just pick one sequence from the first class, the second sequence from the second class, calculate this limit. It will always be the same, right? It will always give you the same limit. Okay, and that limit is the distance between two equivalence classes. That's how we are defining it to be a distance. Is it a distance? Well, it's a distance because first thing is that note it's a limit of distance. Distance is always positive. If you take the limit, it's again going to be a positive number, right? The second thing to note is that, well, if you calculate the distance between x hat, y hat, that's nothing but limit n approaches to infinite, distance xn, yn. But I can also flip this, right? I can also calculate limit n tends to infinite, distance yn xn, right? Because it's symmetric, because the distance function is symmetric. So, and what is this? This by definition is distance y hat x hat, because I started with y and then x, right? I'm taking the nth term of y and then x, so it's distance between y hat x hat. So it's the same thing, right? So it's symmetric. Now the only thing is to calculate, is to check whether the triangle inequality holds or not. Okay, so let's look at that. How do we know, how do we check the triangle inequality? So if you take the distance between xn and yn, I know, so this is just the nth term, right? This is not the sequence, is the nth term of the sequence. Uh, okay, so there's a sequence xn, right? From, let's say, equivalence class x hat, the sequence yn from the equivalence class y hat. Take the distance between the nth terms. You can have a triangle inequality by introducing the nth term of another sequence, Zn, right? Zn, which belongs to, let's say, another class Z hat, right? This is possible. It's just triangle. This is just triangle. Now what you need to do is just take the limit. Just take the limit both sides. So you can definitely take limit n tend to infinite. Here also limit n tend to infinite. Here also limit n tend to infinite. So what that so what is this? The limit n tend to infinite distance x and yn. It's nothing but the distance between x hat, y hat by our definition, right? By our definition. What is this? This is distance between x hat, z hat. What is this? This is the distance between z hat and y hat. Okay, so, well, that's good because the triangle inequality holds for even this distance, right? Even for this function that we have defined as which is nothing but a limit form, but it's a distance because it holds, the triangle inequality still holds. Okay, so that means our space, right, of all Cauchy sequences with this metric, we know now it's a metric because of these three properties. It is a metric space. This is a metric space. Okay, that's good, right? Because now you have a good space, a metric space, right? Now there are other questions. Now how do I know whether the original metric space is in here, right? How do I embed it? Is it there? If so, how, right? And is it complete, right? Is it complete or not? That's a question. That's another question. And is it unique? Is this space unique? So these are the questions that we need to answer. Okay. Okay, so the next part of the proof is to show the original space is in this new space, right? So the original metric space is already there in this space that we created using all those Cauchy sequences, the equivalence class of Cauchy sequences, right? Well, how's that possible? Well, that's possible because if you pick a point from our space, original space X, right? Well, that maps, you can actually map it to another point here. So what are the points here in this space? These are all Cauchy sequences. So obviously the best way to create a sequence is just have this one, right? So a sequence where, you know, every term is the same, it's X, right? So this is a sequence. Now, does this sequence belong to the space? Remember, this is the space of all Cauchy sequences, right? The equivalence class of all Cauchy sequences. Well, is this Cauchy? It is Cauchy, right? It is Cauchy. Why is it Cauchy? Because you look at the terms, they are the same. So, and the distance between any two consecutive terms is 0. It's 0. So it is Cauchy. So this is Cauchy, right? You can actually write this as x hat, right? To represent, it belongs to the equivalence class x hat, right? Containing this particular sequence as one of those sequence, right? And so this belongs to the space, right? With d hat metric. Okay, so that's a mapping, right? And is it isometric, right? Is this item isometric? What do I mean by isometric? That means if you pick any 2 points from the original space x, y, right? This is equal to, well, how have we mapped this one? So the mapping, let me denote this as t, it maps to this constant sequence, right? And so essentially what we need to calculate is, so this is the distance. Now let's calculate the distance between the mapping of x, which is tx, mapping of y, which is ty, right? How have we defined this distance here? This is nothing but a limit n approaches to infinite distance of the terms, right? The nth term in tx and ty sequence, right? So tx is nothing but the constant sequence, right? Which we denoted as x hat. Ty is nothing but the constant sequence y hat. You pick the nth term, it's nothing but x, right? The nth term is x. The nth term from this sequence is y, so it's distance xy. So it's always going to be the same thing, distance xy, and when you calculate the limit, it is nothing but distance xy, right? So these two are the same thing, right? So this is isometry, and this is how you embed the space xd inside the new space that we are creating here, right? So it's the space of all Cauchy sequences with this new metric. You have embedded it. Okay, now this is good. So what we have essentially done is that you have, so we have this bigger space x hat, and we have embedded. Is there something more to this? Well, is it just an embedding, right? Can we have some other properties? Well, there's something called density. What does density means? Or dense? It's not density, I'm sorry. There's something called dense set, right? So in topology, right, or even in when you deal with analysis, you hear dense sets, right? So what are dense sets? Well, nothing but, can you approximate this? Can you can you approximate this entire space using sequences from this space xt, right? So if x happens to be a dense set, what happens is that if you pick any other point from this space, you will have a sequence, right? You will have a sequence from xd which will approximate x, which will tend to x. Well, so the diagram is not well, it can be a little misleading, right? Because if you're just looking at it geometrically, well, this is a circle, I can see a distance between this and all these points inside. Well, how does that approximate? Well, that's the point here. So for dense sets, maybe this is not an appropriate diagram, but maybe a better diagram can be something like, it is dense, so it's scattered, right? It's maybe scattered. This it's densely scattered, right? So, but anyways, it's embedded already. We have seen that it has been embedded, but now it is just scattered. And we can definitely find a sequence in our original space which can approximate x, right? X is any random point, right? You can approximate using this using this dense set. Okay, now is that possible? Yes, it is possible, and I will show the proof of this one. Now, how do I prove that? All you just need to do is pick any point from this space, right? So, well, I should actually write x hat, because it's actually a space of all equivalence classes of Cauchy sequences, right? So distance. So the question is, if I pick a point in this space, let's say x hat, which is a equivalence class of Cauchy sequences, is it possible, right, to have another point here which is extremely close, right? Let me write epsilon, right? Yeah, let's write epsilon. That epsilon is extremely small. Can I have a tiny ball around this point x hat, tiny ball, yet I will find another point from the embedded dense set, right? Let's assume this is the dense set. This says xd. We have already embedded it, but is it dense? If it happens to be dense, then you can definitely find a point, right, from the space which is extremely close to x hat, right? So distance x hat and a new sequence, right? So let me denote it like this. Maybe it's a bad notation, but something from this original space which is extremely close to this new point, right? Is it really possible? Well, yes, it is possible. It's definitely possible to find such points, even whatever epsilon is. You can definitely find things close to x hat. How you do it is by the property of x hat, because x hat is a class of Cauchy sequences, right? So let's pick one sequence from that equivalence class that's Cauchy. So we know that distance xn, and let me pick a point n, capital N. This can be made less than, well, you can write epsilon by 2, epsilon, it doesn't matter. It's a small quantity here. You can make this extremely small or less than epsilon by 2 for all n bigger than or equal to n, right? So this is by Cauchy, right? This is by the property of Cauchy sequence. Cauchy sequence, right? So for large n, you can definitely find an n such that xn and x at nth term, the difference or the distance can be made less than epsilon by 2, right? This is just by Cauchy sequence, right? It's by Cauchy sequence, so you can make it extremely small. Now the question is, so if I calculate the distance between, so what's the other point, right? So so you have x hat here, right? I need another sequence. So I will construct that sequence as follows. So let's take that sequence to be xn, right? So all the term is the same thing, xn. And now let's calculate the distance between xn, or I shouldn't say xn, I should just say x hat and xn hat. Okay, so what's xn hat? It's that, so this sequence belongs to xn hat. It's that equivalence class of all the Cauchy sequences. This is also Cauchy, which you get by mapping this xn point from this metric space, right? From this metric space, you constructed this. This is here in this xn hat equivalence class. Okay, so that distance between these two equivalence classes is nothing but a limit and tends to infinite distance between xn and this equivalence class has this particular sequence. Everything is the same, n xn, right? So if we calculate the limit, well, the way we created it, right, it's that it is less than epsilon by 2. So you can actually make it less than epsilon by 2, or it's already less than epsilon by 2. Even if you take the limits, it's less than epsilon by 2, right? So this quantity that you see here, distance between x hat and xn hat, can be made extremely small, right? You can make it extremely small. Well, these sort of sequences are there in the these are like the images of our original space, right? XD, the way we embedded it. The way we embedded it is using the mapping Tx, which is nothing but all the constant sequences, right? So you can definitely find a point from that image which is extremely close to this point x hat. Okay, so hence this is also dense. It's also dense. So this implies the image xd, or you can say xd is dense in this space. That's good. Density is good.